Hello from the Forcetronics YouTube channel and welcome to designing a thermocouple based temperature measurement circuit part 2. And this will just be a series of 2. If you haven't seen part 1 yet, I recommend you do that first before you watch part 2. Before I get started, I'll mention please check me out on Facebook, Twitter. Subscribe to my YouTube channel. If you like what you see here in this video, please hit the thumbs up. And check out Forcetronics design and consulting services at forcetronics.com. All right, let's get started. Okay, in part 1, we went through thermocouple measurement theory. We briefly went over the thermocouple types and an overview of some of the measurement hardware and software calculations that are needed to do a thermocouple temperature measurement. In part 2, we get into more of the real-world design. We'll step through how to put together a thermocouple hardware design circuit and look at some of the techniques out there to reduce measurement error. Because thermocouples use very small signal levels, measurement error for your temperature measurements can be a problem. So we'll talk about how to avoid some of these sources of error. And I'll tell you from firsthand knowledge. Okay, this is the slide. This is the last slide, or one of the last slides I covered in part 1. And this just kind of shows the overview of the blocks from a hardware standpoint and some of the calculations from a software standpoint that's needed to take this really small voltage that's generated by putting two dissimilar metals together. And remember, they're put together at the point where we're trying to measure temperature, and then the pieces in between that are needed to get to that temperature measurement. And some of the critical ones are the fact that we have this reference junction where our thermocouple wires meet our circuit, and so that creates another dissimilar metal connection. So we need to compensate for that, and we do that by monitoring the temperature at that reference junction. Our signal is very small, so we're going to need to amplify it. We're going to need a high resolution ADC typically to capture it, and then we'll need some calculations to get the final answer. But as I concluded in part 1, I wanted to provide you an overview of all the pieces that are needed to make the measurement. But luckily, there's a lot of off-the-shelf ICs that are targeted for thermocouple circuits or thermocouple measurements that have a lot of the blocks that I just showed you built in. So this is not supposed to be an exhaustive list. This is just 2 examples. The MAX 31855 from Maxim Semiconductor. This is targeted at thermocouples. It has a built-in reference temperature sensor, a built-in ADC, and it communicates the results out on a 3-wire SPI line. So this is a truly analog to digital type solution where everything is incorporated in the IC. And then another example is Analog Devices makes the AD8494. This is another amplifier with a built-in temperature reference, right? So both these ICs have an amplifier in there. For the Analog Devices, they call it an instrumentation amplifier. An instrumentation amplifier is typically an op-amp that's made for very high precision applications. So they'll have low drift, they'll have low offset error, things like that. And it has a built-in thermocouple cold junction compensator. It supports both J and K type. And basically it's an all-in-one but analog output IC, where the first one was a digital output. This one provides a 5 millivolt per degree output that you can measure with an ADC on a microprocessor or a microcontroller. I'm going to dive into the AD8494 example with J Type and show you an example circuit that I had to create. And the reason I went with this one is because for the project, there was already an existing microcontroller board that I was interfacing with that had free ADC pins but didn't have free digital pins. So for this application, I needed an analog output to measure the temperature. So here's a little more detailed overview of the AD8495. And there's a couple different versions of them. I think it's the the 94, 95, 96. Some were targeted more towards J-type thermocouples. Some are targeted more towards K-type thermocouples. Overall, they're very similar. So once again, built-in instrumentation amp with a set gain. And basically that set gain delivers that 5 millivolt per degree output. It has temperature compensation, so basically it has a built-in temperature sensor to measure the temperature at the reference point. The reference point is where the thermocouple wires join the circuit. One thing to note is the temperature sensor is built into the IC, so we want to make sure the thermocouple connection is close to the IC. The chip also has options for filtering. I'll talk about that because, once again, this is a very low-level signal, so it's very susceptible to noise. You could have a dual or a single power supply with a reference. Let me get into that real quick. The power supply has, I forget the range, but let's just say we're having 5 volts. With 5 volts and with the negative supply tied to ground, we basically get 0 to 1,000 degrees Celsius range. And that means, and we can do the math there, 5 volts, 1,000, so 5 millivolts per degree. But we could also expand that range or shift that range. So we could expand it by adding a negative power supply, and that way we could measure negative temperature. Now, there's limits what we can do, right? Because there's the limits to the range of the thermocouple itself. But we could measure a larger range with a negative power supply, but then we also need an ADC that can measure negative voltage, or a differential ADC. Another thing we can do, though, is we can use the reference pin right here. So, for instance, if we got an off-the-shelf voltage reference that was, say, let's say it's 1 volt. Commonly, they're not just 1 volt, but let's just say it's 1 volt. Well, we can shift the range. So with a 1 volt reference, at 0 volts, we get negative 200. So 0 volts would be negative 200 degrees Celsius. 5 millivolts would be negative 99 degrees Celsius. And then we could go all the way up to 800. So we lose some of our top range, but we shift it into the negative value. So we have some flexibility, I guess, on what range we want to measure with this type of IC. Now, as I mentioned, one of the tough things designing a thermocouple circuit is accuracy. In general, thermocouple is not a highly accurate way to measure temperature, right? Remember, the benefits are its huge temperature range and its ruggedness and its ability to handle very high temperatures as well as very low temperatures. So since it's already not a very accurate method because of the low-level signal and different error sources, we need to make sure our circuit is very clean so we don't add additional error. So the 2 main sources of error are noise and temperature variations between the IC and the reference junction. So noise. Remember, we're dealing with, if you remember from part 1, microvolt, tens or hundreds of microvolts change represents a degree change. Now, with this IC, we're amplifying up to 5 millivolts, but you're dealing with a very low-level signal. So if you have a switching power supply or an antenna or something like that near this circuit, you can cause drastic errors or even bad PCB layout. I mean, some of the things are obvious. We don't want to put this near a switching power supply. We don't want to put this near high-speed digital signals and share the same ground plane. And by the way, if you're not familiar with good PCB layout practices and noise and ground planes, I do have a video series on that. And it's very applicable to this series because it talks about sensitive circuits and how to prevent that with good PCB layout techniques. Now, the chip itself provides recommendations for input filters, which I think is nice. And I'm not going to go through these calculations, but for differential noise as well as common mode noise, they provide this filter and these equations. So if you might know some of the noise sources on your design and their frequency range, you can tune these components as best as you can to the noise they might encounter. Now remember, the lower the frequency these are, the less you can handle quick dynamic changes or make measurements, so keep that in mind. And that gets me into temperature variation. You might say, well, why is that a problem? Well, the issue is the AD8495 has a built-in temperature sensor. But if you don't have your reference point or reference junction close to the chip, or there's a temperature variation between the chip and the reference junction where the thermocouple cables are connecting, then you're going to have error because that temperature sensor inside the IC is serving as the reference junction compensation. It does it automatically, but we have to keep that in mind that they have to be at the same temperature or it's going to be a major source of error. what could cause this? Well, the thermocouple junction is not close to the IC. I mentioned that. Another thing is look at the heat sources on your board. You want to keep this away from the heat sources that could cause uneven heating on the board. So a perfect example is a linear power supply. So if you notice, I'm saying a switching power supply is bad because of noise, but a linear power supply is also bad because of heat. But if you have to use one of those, we just have to make sure we use good practices. For a linear power supply, we want it far away, we want the ground plane isolated, and we may even want to have multiple stages of linear power supplies to reduce that power drop across the power supply that's going to lead to heating. Okay, we'll look at some example of some good ground plane layout to reduce noise and temperature variations. But these are the main sources of errors, and I know firsthand I'll share a story about a design where temperature variation got me into trouble. Okay, what I'm showing you right now is a schematic from Eagle, which is a PCB layout software. And I'm just showing you I have two thermocouple channels, and I'm showing you my design as an example. Here are my two AD8495, so I have two channels. We call it T1 or TH1 and TH2. This is the connector for the thermocouple cables. And then here is these are sort of current limiters, but this is my filtering network. And I'm not going to go through these equations, but I chose it for a little higher frequency reduction. Then here is the amplifier itself, and then here is the output. And then this is just an identical circuit for a second thermocouple measurement. Now what makes this circuit a little different is I have two other stages of amplifiers. So TH1 gets this output from here, feeds it into this amplifier, and then vice versa for this one. Why do I have two amplifier stages? Well, I mentioned for my application, I have a built-in, and I'm integrating this into an existing design where I have a microcontroller, and that microcontroller only has 10-bit ADC channels. If you only have 10-bit ADC channels and you're trying to measure a signal that represents degrees in 5 millivolts, that's not a lot of resolution in your ADC measurement to capture the difference between 1 degree or another. Now you can change that a bit by adjusting the voltage reference of the microcontroller, but you still don't have a great amount of resolution with a 10-bit ADC, especially since 10-bit ADCs are really have an ENOB of 9 or 8 bits. So that wasn't going to do for this type of output from this amplifier, but at the same time I couldn't change the microcontroller. So what I did is I added a second amplifier stage. This is an instrumentation amplifier. It's not targeted at thermocouple measurements, just targeted at sensitive measurements. And what I did is I set it up for a times 7 gain. So here's and once again, I'm assuming you know the basics of an op amp. 2K to 12K is 6 plus 1, that's my gain 7. So I'm taking that 5 millivolt representation or the output of this and multiplying it by 7. So now each degree is really 35 millivolts instead of 5 millivolts. Note that I have these bypass caps for the power supply input to try and, once again, I keep them close to the IC because I want this to allow power supply noise to go to ground. Now I'm using a linear regulator in this design, so it's low noise but high heat. If I was using a switcher, I probably would have even more capacitors here, maybe even a ferrite bead or something like that to further reduce the power supply noise. Okay, let's look at the layout. Okay, so I'm going to show an example of a bad layout, an older version, and then I'm going to show you what I did to correct it. So I did this first pass of this circuit, and I noticed after the device was on for a while, or the design was on for a while, the thermocouple temperature would drift up, even though the temperature it was measuring was not changing. And I was like, uh-oh, why is this drifting up? Well, first of all, let me explain this layout. This is a 2-layer board, so I just can route signals and ground plane on the top layer or the bottom layer. And what I did is I have the top layers in pink or red and the bottom layers in blue. And what I did is I did these cutouts because, once again, if you're familiar with ground planes, is whenever on a PCB board you have a trace, you have current flowing in certain instances. Well, guess what? That current has to return to its source, and it does that through the ground plane. So what I did is I cut out the ground plane here and here to prevent signals from other circuits flowing through this area and possibly, and when they flow through the ground plane, they create a magnetic field, and that magnetic field could get onto sensitive traces and cause error. Once again, I have a video series where I talk about this in more detail. So that's why I have these cutouts. Now, I didn't do any cutouts on the bottom ground plane, but I did cutouts on the top, and I added these vias sort of around the circuit to help protect it from noise. I have it far away from the power supply and other noise sources here on the corner. Here are my connectors. And what I noticed was temperature drift up when it shouldn't have been. Well, guess what? I figured out that it's from the linear regulator. So way up over here, I have a linear regulator. And what was happening is as the linear regulator heated up, it heated up the ground plane. And so that thermal heating would spread through here into this circuit. And if you notice, U6 and U8 are my thermocouple amplifiers. U7 and U9 are the instrumentation amplifiers with the gain of 7. Well, if you notice, U6 and U8 have ground plane right underneath them. So that ground plane would heat up and that internal temperature sensor would heat up. But when the thermal effects spread over here, this is a plastic connector with metal inside, it didn't heat up the thermocouple wires as much as it heated up the IC. So the reference junction thought this temperature sensor thought the temperature at the reference juncture was higher than it was, so it caused the reading to be off. And you could even see the difference between T1 and T2 because this amplifier is farther away from the linear regulator than this one. So they would both rise, but the one that was closer would rise a little bit more. And one of the ways I tested this was I said, okay, I think this is the problem. I took a heat gun, I turned it on, I pointed at the linear regulator, and I could quickly see the temperature rise on my thermocouple readings. I then removed the heat gun and I pointed it at my thermocouple wires, not at the board, but at the thermocouple wires right before the connector. And guess what happened? The temperature of the thermocouples dropped below the ambient temperature, or the temperature being measured, because I made the actual reference junction hotter than the reference junction I was measuring. So anyway, that's a real life story. So I had to redo this board. So here's my updated design where I corrected the thermal spread problem. So this is the same schematic, just the board layout is different. And so I did two big things, right? I just cut out the ground plane here to really isolate both the top and bottom. And if you're familiar with PCBs, this other piece is in between is the RF4 material, which is an insulator. So it's not a good conductor of thermal heat. So I removed the ground plane both on the top and bottom. And the only place the ground plane connects is these places right here on the bottom ground plane. Now you might say, well, you could get a ground loop. You could get ground currents flowing through here to here. But these circuits above this really don't have high current. And I only connected the bottom ground plane. The top ground plane is only connected via vias. And then the other thing I did was I removed even the local ground plane from underneath these ICs. So they're touching the FR4 material, which once again does not conduct thermal heat as easily. So, and I even moved these closer to the connector. It's hard to tell, but they're even closer now to the connector. So once again, removing the ground plane right underneath the ICs, isolating this circuit's ground plane from the linear regulator really solved my temperature problem. So that's a real life example of some of the trouble I had. Okay, the last thing I wanted to touch on just to be complete was how do you test your design? Because temperature measurements are in nature not hugely accurate. So if you do a thermocouple design, how do you verify it's correct? It's not as easy as you think. So one thing you can do is I talked about the ice bath. So you could set up a thermocouple setup with an ice bath, and you could use a DVM, high resolution, 6.5 digit. DVM stands for digital voltmeter, or a DMM, digital multimeter. And the idea is I can use the high resolution of the DVM and the tables from places like NIST to measure that low level voltage with a known reference temperature and use that to compare it against my thermocouple circuit. So I can do that as a controlled standard to test how accurate I am, or at least that I'm working correctly. So that's one way to go. Another way to go would be to simulate the actual thermocouple signals, not with a thermocouple wire, but with an external source. So if I have a DAC or something like a function generator where I can output DC, I can output the thermocouple signal and check my circuit and see if it's getting the right temperature. Most DACs or function generators won't be able to have the type of resolution to do, differences of 100 microvolts or tens of microvolts. So what you could do is you could use a voltage divider circuit to divide the voltage down further and then feed it into your thermocouple circuit. Once again, if you have a high resolution DVM is typically more expensive. You can buy, as a hobbyist, you can buy those handheld cheap ones. That's not what I'm referring to. I'm referring to more of a high resolution one that can measure microvolts. So you can use that to verify your DAC's output, and that way you know exactly what's going into your thermocouple circuit and what temperature should be coming out the other end. Another thing you can do, and I did a sort of a combination of these, but you can just add a bunch of other reference temperature sensors. So I did a thermistor and I had a temperature measurement IC. I put them both by my thermocouple probes as sort of a reference. And the reason you want to do that is, once you're doing your testing, I had all my equipment at the bench turned on. The temperature in the room naturally rose a little bit. So you want to use your reference temperature sensors to know that it's the actual temperature rising and not your circuit. Now, the downside to that approach, of course, is thermocouples can handle very harsh temperatures. This sort of eliminates that or doesn't allow you to do that because you're using temperature sensors that can't handle harsh values. Okay, that's it for part 2, designing a thermocouple-based temperature measurement circuit. So if you have anything to add or you think I missed anything or you want me to expand on anything, use the comment section. If you have questions related to this, use the comment section. And thank you for watching.